In this lecture, we're going to discuss the solvents used in SN2 reactions, and those mysterious things, I guess, I've been putting over the arrow. So again, what we have is we have A plus B goes to C, I guess I called goes to D plus E. And the thing I was putting over the arrow C, that's the solvent. So this helps facilitate the reaction, but it doesn't directly contribute to the elemental composition of the product. So we don't really want to call it a starting material. We don't do too much in the way of stoichiometry on it. Like I rarely calculate the moles of solvent that I add. I usually just am more concerned with the volume. Anyway, what types of solvents work? So we need a solvent that will first of all, not react with anything. So reactions are things where we make and break covalent bonds. So the solvent, we don't want it to break / make covalent bonds. If it's doing this, then it will be a reactant in the reaction. And so for us to really be able to control the reaction of one electrophile with one nucleophile, we want the solvent to do its thing without making or breaking covalent bonds. It will disrupt ionic bonds to, as we talked about in the last lecture, to make sure that the anionic nucleophile, often an anion, can react properly with the electrophile. But it needs to, so it can't react with anything, but it must dissolve everything. Okay, now what this gets to is a term called a polar aprotic solvent. And this is what's required for SN2 reactions. Okay, so polar and aprotic. So the polar, that comes from something with a permanent dipole. Spelled that wrong. So it needs a permanent dipole. What this allows for, it allows for intermolecular attractive interactions with all reactants. Now, actually the haloalkane doesn't worry too much about if the solvent is polar. It just needs to not be too polar, like in the case of water. But it needs to be polar enough to dissolve the thing that's hardest to dissolve, which is our nucleophilic salt. The nucleophile salt, which is M for metal, nuc for nucleophile, where the metal is our counter ion, and the nuc minus is our nucleophilic anion. So the salt, the combination of the anion and the cation, that's the thing that's difficult to dissolve, and that's the thing that we really need to be careful about our solvent choice to make sure that everything productive happens. If we're polar enough, then the anion can form dipole anionic interactions between the solvent and the nucleophile. So polar solvents can provide, in this case, delta plus interactions on the solvent. They can interact productively with the negative charge on the nucleophile, and that enables dissolving. If you don't have a permanent dipole, then you don't have permanent spots where you have delta pluses and delta minuses, and it's those delta minuses that are so critical for interacting productively with the nucleophile. Similarly, it's the delta pluses that are critical for, it's the delta pluses on the solvent that are required for interacting with the anion of the nucleophile, and the delta minuses on the solvent that are required to interact with the cationic counterion. So that metal counterion also needs to interact with the solvent. It does so with the delta minuses on the solvent. And similarly, so I'll write that down too. It's the delta minuses that interact from the solvent. And these are permanent dipoles, so those delta minuses and pluses are fixed based on the nature of differences in electronegativity amongst the covalent bonds in the solvent. Anyway, back to my point. So it's the delta minuses that interact with the positive charges on the counter ion. Okay, so if we're polar, we've got permanent delta pluses and delta minuses, and we can dissolve the hardest thing to dissolve, which is the nucleophile. At the end of the day, the salt byproduct might be the hardest to dissolve, but I don't really care about dissolving it. In fact, maybe I don't want to. I can let that precipitate out of solution. Okay, anyway, once we can dissolve the nucleophile, we need to accomplish another thing, and the other word I provided was aprotic. So we have the A prefix to the word protic. Last time we saw that was when we were talking about achiral. So achiral molecules are not chiral. Aprotic molecules are not protic. Now, protic refers to acidic or H plus donating, because acidic can take on different terms. We don't say acidic. First of all, it sounds awkward. But aprotic specifies that the type of acid that we're worried about is something that donates H pluses around. Okay, so we have polar aprotic. Now the aprotic is important because many nucleophiles are basic. And one of the first rules, I'm just going to, the first rule that we had for the solvents at the first page of notes for this lecture was it needs to be unreactive with all of the reactants. That is, it cannot contribute to covalent bond breaking or formation with any of the reactants. So many nucleophiles are basic, and the nucleophile, we can't have then the nucleophile reacting with an acidic hydrogen on our solvent. So if we had a delta plus, and the negative charge in the nucleophile could engage the positive charge in the solvent, we need to make sure that that doesn't happen. Because if it does, the solvent would be reacting with the nucleophile, and we can't have that. Solvent can't react with anything. So if we're aprotic, then we can't provide that H plus or that proton. Remember, an H plus is just a single subatomic particle, a proton. If you do its electron configuration, doesn't have any neutrons for most H. I mean, if it's H, then it doesn't have any neutrons because it's that isotope. Anyway, protic means H plus donating. Aprotic means no H pluses to donate. There will be no acid-base reaction between the solvent and the nucleophile. And that's important because the solvent, all it's supposed to do is get everything to dissolve, get the ions to separate, allow things to start to collide appropriately. It's the facilitator, but it's not going to get involved with any bond-making or bond-breaking events at all. Okay, so we're aprotic, we're not reacting with anything. Now what this leads to is some examples of good, i.e. polar aprotic solvents are, and I'll be honest, these are good things to refer to. You'll get more comfortable when you see these down the road, but you don't necessarily need to make flashcards about this at this point anyway. So this is acetone. That's a really good solvent. And this is really good solvent for the purposes of being polar and aprotic. We're learning about, especially things like DMF, we're learning about ways to replace these things with more green solvents. So there's DMSO. We have a sulfur atom. Sulfur can actually hold up to 10 electrons if it needs to. I'll draw it in this depiction. Somebody else might draw it differently, but that's DMSO. And then to a lesser extent, you could see molecules like THF. So these are good solvents. So my point of showing you this is if you see acetone, DMF, DMSO, or THF over the arrow, just kind of say, all right, Willoughby gave us a good solvent. Now, I'm not really in the business of tricking you. I may ask you to propose a good solvent to use, in which case you could just grab one of these four, preferably the first three on this list, using either their structure, which is preferred, or their abbreviation, which is fine. Now, what I want to also do is talk about some categories, some of the other categories. So we have polar, that also means that we could have non-polar. We have aprotic, which means we also could have protic. So let's talk about polar protic solvents next. And we'll use these for a different class of reactions, not the SN2 reactions, but polar protic solvents are polar solvents, so they have permanent dipoles. Permanent dipoles, and they can donate, or they have acidic hydrogen atoms. And that would be protic. So the examples here that we want to keep in mind are alcohols and water. There are many others, but alcohols and water are the big ones. So you have ROH or HOH. You have dipoles with delta pluses and delta minuses that allow us to interact productively with, so this does half the battle that the previous solvents did, the polar aprotic solvents did. These things can dissolve nucleophiles very well, but the problem is they then react with the nucleophiles because we now have acidic hydrogen atoms. So water has 2 acidic hydrogen atoms, whereas alcohols will have 1 acidic hydrogen atom. So we have polar aprotic solvents. We next have non-polar solvents. And we won't consider aprotic and protic categories for the non-polar solvents. So we just have non-polar, then polar, and there are 2 classes of polar solvents. There's polar protic, where we can donate a proton, polar aprotic, where we don't have an acidic hydrogen to donate, and then just non-polar by themselves. So, and the reason why is most non-polar solvents are aprotic. Like it's impractical for our discussion to use things that are protic and non-polar. So most are aprotic. So we just don't even include that classification. And when I say most, I mean most, vast majority are aprotic. Anyway, okay, so we have most are aprotic, and these are usually, for our purposes, hydrocarbons. And the reason why is if we're not polar, we have no permanent dipole, which means no difference in electronegativity. So since we have no difference in electronegativity, we have no permanent dipole. We're going to see these for hydrocarbons. So there's an example as octane. Hydrocarbon solvents have their place and their purpose, particularly in chromatography. In reactions, you have to sometimes be wary about using fully nonpolar solvents, definitely when you have salts. You just won't see these things dissolve or interact because they can't form these dipole anion-cation interactions to facilitate the dissociation of the nucleophile salt. And as a result, you just, because of that, if you don't see dissociation, you don't see reaction. And so you don't see use for these things. SN2 reactions, the reaction we've been talking about so far, that'll for sure use a polar aprotic solvent, something that can dissolve the nucleophile but not react with the nucleophile in an acid-base reaction. So in this lecture, we looked at the solvents that can be used, these things that go over the arrow. There's not a whole lot of me asking you to memorize the particular structures, but I do want you to be able to appreciate the different classes and be able to recognize when something is a polar protic solvent, for example. That is something that's an alcohol or water. Just be able to notice when you see polar protic, and then know that we use polar aprotic solvents for SN2 reactions and the reasons why we use them. Okay,